Hey everyone, and welcome to This Explainer. I am so thrilled you're tuning in because today we're going to take the invisible and make it visible. We're diving headfirst into the completely fascinating, totally unseen world of wave mechanics and acoustic physics. Seriously, this is the secret architecture that dictates absolutely everything around us, from the colors popping on your screen right now to the music you listen to.
Now, to kick things off, we need to start with a massive, fundamental question. How exactly does energy travel without moving matter? It's kind of a total mind-bender, right? Because we're so used to having to physically throw an object, like a baseball, to move energy from point A to point B. But the totally counterintuitive reality of our universe is that waves transport immense amounts of energy across vast, vast distances, while the physical particles themselves, they barely go anywhere. They literally just oscillate or vibrate right in place.
All right, so here's our roadmap for today. We'll start with 1, the nature of waves, then move to 2, the anatomy of a wave, look at 3, how waves behave, dive into 4, the science of sound, and wrap up with 5, sound in the real world.
Okay, let's jump straight into part 1, the nature of waves. So what is a wave, really? At its core, a wave is simply a disturbance that transfers energy from one place to another without transporting matter permanently. Think about it like this. The energy is the thing actually moving, while the medium itself is just passing that disturbance along. It's exactly like a crowd doing the wave at a sports stadium. The people aren't running laps around the entire arena, right? They're just standing up and sitting down in their fixed spot.
Now, as you might guess, not all waves are created equal. We essentially have 2 massive categories we need to understand. First, you've got mechanical waves. Think of the sound of my voice or ocean waves. These absolutely require a physical, material medium to propagate. They literally need matter to ride on. On the flip side, we have non-mechanical or electromagnetic waves, like light or X-rays. These are the ultimate independent travelers. They don't need a medium whatsoever and can actually travel straight through the completely empty vacuum of outer space.
Moving right along to part 2, the anatomy of a wave. To actually measure these invisible forces, we use a very specific physical vocabulary. Just imagine a single rolling wave for a second. The physical distance from one crest to the next, that's its wavelength. How rapidly those crests are passing you by every single second is the frequency. The time period is simply how long it takes for just one complete oscillation. Now, the sheer height or the physical intensity of that wave is its amplitude. And tying the whole thing together is the golden rule of wave propagation, wave speed. That velocity simply equals frequency times wavelength.
All right, part 3, how waves behave.
When waves meet the physical world, they're surprisingly predictable. If a wave hits a surface, it's going to bounce back through reflection, and it'll always leave at the exact same angle it hit. If it passes into a totally different medium, like light bending when it enters water, that's refraction. When waves run into obstacles or squeeze through narrow openings, they fan out through diffraction. And finally, when 2 waves literally crash into each other, we get interference. They'll either perfectly align to construct a much larger wave, or they'll clash and destructively cancel each other out completely.
Now let's get into the stuff we hear every day. Part 4, the science of sound.
Let's lock down an exact definition here. Sound is, specifically, a mechanical longitudinal wave produced by vibrating objects. And remember what we said earlier? Because it's a mechanical wave, it strictly requires a medium to travel. It travels fastest through the tightly packed molecules of solid objects, much slower in loose gases like the air we're breathing right now, and, here's the kicker, it absolutely cannot exist in a vacuum. Literally, in outer space, no one can hear you speak.
So how does all this pure physics translate into our actual biological senses? Well, the frequency of a wave directly dictates the pitch we hear. So higher frequency physically means a higher pitch. The amplitude dictates the loudness we feel, which we measure in decibels. And finally, the complexity of the waveform itself gives us quality or timbre. This is exactly why a piano and a guitar sound completely different to your ear, even if they're playing the exact same note.
Let's talk about the biological boundaries of our own human ears for a second, starting with this number, 20. 20 Hz is the absolute lower limit of human hearing. Any mechanical wave vibrating fewer than 20 times per second is considered infrasonic. Now, you might actually feel it as a weird deep rumble in your chest, but your ears simply cannot process it as sound.
And on the totally opposite end of the spectrum, we have 20,000 Hz. That's the ultimate upper ceiling of human hearing. Anything above that is ultrasonic. So, you know those silent dog whistles you see at the pet store? There is no magic happening there. They're literally just physics formulas in action. They emit super high-frequency waves that human ears completely fail to catch, but a dog's ears pick up with no problem at all.
But what actually separates beautiful music from, well, irritating noise? It all comes down to the wave structure. Musical sound is created by regular, periodic vibrations. They're mathematically organized, making them pleasant to the ear. Noise is the exact opposite. It's just irregular, chaotic vibrations causing unpleasant sensations. And when stuff like traffic or industrial machines produce way too much of this wave chaos, we end up with noise pollution, which is a real problem that requires serious soundproofing and engineering regulations to fix.
Which brings us to our final section, Part 5, Sound in the Real World. First up, we've got the Doppler effect. This is a change in frequency due to relative motion between a source and an observer. Honestly, we have all experienced this. Think about an ambulance racing toward you. The sound waves actually physically compress and the pitch goes way up. But the second it speeds past and drives away, those waves stretch out and the pitch dramatically drops. The physical motion of the vehicle is literally shifting the frequency you hear in real time.
Now, let's talk about the sheer destructive power of resonance. Resonance occurs when a system vibrates at its natural frequency because of an external force, which leads to massive amplitude vibrations. This is exactly the acoustic physics behind a singer breaking a wine glass with just their voice. By hitting the perfect natural frequency of that specific glass, the sound wave's energy just compounds and compounds until the physical structure literally shatters. It's wild.
And the coolest part is, we harness these exact acoustic formulas for incredible, tangible things every single day. In science and tech, we use high-frequency ultrasound for medical sonography. In exploration, we bounce sound waves to map out the pitch-black ocean floor using sonar. Engineers are using sound right now for structural testing to detect invisible cracks inside solid metal. And obviously, in our daily lives, it's the entire foundation of human communication and music.
I want to wrap up by leaving you with this thought. Understanding waves explains how we communicate, detect objects underwater, and explore the universe. You see, these aren't just dry equations sitting in a textbook. These are the invisible, powerful forces that shape our entire reality. And once you truly understand the physics of a wave, you kind of have to ask yourself, what other invisible forces are shaping the world around you right this very second? Thanks so much for joining me on this explainer, and keep learning.